When looking at the motion graphs of a spring that is bouncing back and forth and a pendulum at an angle of less than 15 degrees swinging back and forth, we see that their motion graphs have very similar shapes. Their position graphs all take a sine or cosine type shape. Their velocity, being the slope of the position, also is a trig function. If my position graph was a negative sine graph, for example, then my velocity, being the slope of that, would actually be a cosine graph. And my acceleration, being the slope of velocity, would in fact be a sine graph. Please notice that my position graph and acceleration graphs are actually opposite shapes. That was the same case that we had seen with the spring before, and that's what we're seeing with the pendulum as well. And again, this is why people are very willing to say that a pendulum acts like a oscillator, because its behavior is very similar to that of a spring, especially when looking at its motion. Since the tangential acceleration of the pendulum is not constant, it's constantly changing both magnitude and direction, the big three equations of motion that we have worked with in the past cannot be used. Remember, this was the same thing that we had with the spring. Because the acceleration is not constant, we cannot use the big three equations that we've used from the beginning of the year, because the only requirement to use those equations is a constant acceleration in both magnitude and in direction. Period is a concept that we've worked on throughout the year, and just to recap, it is how much time it takes, or it's the period of time for a cycle to repeat itself. If we're looking at a spring, for example, it is the amount of time that it takes for a spring to start at one amplitude position, travel all the way to the opposing amplitude position, and very importantly, return back to the starting position. If I'm looking at a pendulum, it would be the time it takes for a pendulum to start at one amplitude position, swing all the way across the other side to the opposing amplitude position, and very importantly, return back to its start. That is why when we take a look at a sine or cosine graph, it would be the time it takes to go from one peak to another peak, or from one trough to another trough. It is never the time it takes to go from one side to the other. That would in fact be only 1/2 a period. So to swing from one side to the other would be only 1/2 a period. If I was swinging to the bottom of the swing, that would then only be 1/2 of a half, or 1/4 of a period. And remember, while period is in fact the amount of time it takes for a cycle to repeat itself, or the amount of time for a given number of cycles divided by the number of cycles, frequency is in fact the exact inverse of that. It is the number of cycles that occurs in one moment of time. So it's the number of cycles divided by the amount of time you have for those cycles. Frequency has always been the inverse of period. And again, that means if I have a high frequency, something's happening a lot very frequently, then they have a very short period, a very small amount of time to make that happen. However, if I have more time to let something happen, then it happens less frequently, so the frequency is lower. When looking at a pendulum's period or frequency, there are some things about the pendulum that definitely affect these things, and there are some things that just do not. Just like with a spring, there were some aspects of a spring mass system that affects the period, but there are other things that did not. And since a pendulum is not a spring, those factors are not necessarily going to be the same. For example, mass does not affect the period of a pendulum. If gravity is the driving force, then the driving concept behind this is the fact that all things will accelerate at the same rate regardless of their mass, because mass has no impact on your acceleration due to gravity. And with a pendulum, just like Galileo first noted, the heavier masses swing just as fast or slow as the smaller masses. This is very different than for a spring, but then the force of a spring is independent of the mass of the object that it's pulling on. The force of a spring depends only on the distance the spring is pulled and the strength or the spring constant of the spring itself. For gravity, it depends on the mass of the object. So the inertia aspect cancels out the force aspect, and that's why we always have the same acceleration when you fall or swing as a pendulum. So again, just to illustrate this and to stress it, the mass of a pendulum is independent of the acceleration, and the core reasons are Newton's first and second laws of motion. Predominantly, people will view it as the second law of motion because it is the most mathematical representation, that since the acceleration is equal to the net force on the object divided by its mass, and the net force along the tangent aspect of the pendulum's motion is Fg sine theta, that divided by the mass will just give you acceleration of gravity sine theta. Mass cancels out. So greater masses experience greater forces, but greater masses also have greater inertia, greater resistance, and so the period does not change. Another factor that does not affect the period of a pendulum while it's imitating simple harmonic motion is the angle of the swing. There is a catch on this. This is true if the angle is less than or equal to 15 degrees. But remember, if you're beyond that, then you're not going to act like a simple harmonic oscillator. But if you're underneath this restriction, then the angle does not affect the period at all. And this makes a lot of sense because larger angles have a greater acceleration because the acceleration is ag sine theta. And as theta approaches 90, sine theta gets larger. So I'd have a very large acceleration if I have a large angle, as versus I have a small acceleration over here. But the distance I swing through with a larger angle is greater than the distance I would swing through over here. And that's because the arc distance is equal to 2 times the theta that I pulled the pendulum back at times the length of the pendulum. Well, you might be thinking to yourself, well, I thought S equaled theta r, and S was my arc distance, and theta was my angle. That is true, but theta is the angle from radius to radius in this particular case. That's 2 times the angle that you're being pulled back at. So this theta in this equation represents a different angle than this one here. So you have to be kind of careful with that. The radius of the arc is in fact the length of the swing. One of the first uses that we had for pendulums was actually that of a clock that was driven by a swinging pendulum back and forth. The reason for this is because the amplitude of the swing has no impact on the period. So this is a wonderful timing device. In the beginning of the day, when I prep up my clock, the pendulum will swing back and forth. It will have a very large swing. And as it wears down throughout the course of time, it sways very little. But the accuracy of the clock remains the same until the pendulum stops moving completely. Now, one of the factors that do affect the period of a pendulum is the length of the pendulum itself. Please notice that for a spring, there was no relationship between period and length of the spring, but for a pendulum, it's very different. The major reason for this is because even though the string might be longer for the red bob than the blue bob, the angle for both of these is exactly the same, which means they both experience the same tangential acceleration of ag sine theta because they are at the same angle. But because the lower bob has a longer radius, it does travel a longer distance than the short pendulum. So now this bottom pendulum is traveling a greater distance, but with the same acceleration. Thus, it's going to take more time for a longer pendulum to swing than a shorter pendulum. Again, we can see that right here, that the acceleration of the pendulum is ag sine theta. And the only thing that is going to determine this acceleration is the mass of the planet that you are on, the distance the pendulum is from the center of that planet, and the universe in which you are in. Thus, the actual pendulum itself does not affect this acceleration, with the only exception of that angle. This is why we say that the acceleration of gravity for the planet that you are on affects the pendulum. This is why if you had a pendulum clock that's swaying back and forth on the planet Earth and it kept perfect time, and then you took that clock to the moon, it would actually run wrong. The pendulum would swing too slow. The clock would run slower than it should, for the very simple reason the acceleration due to gravity on the moon is much less than that on the Earth. Again, just re-illustrating and restating this very important point on this, based on Newton's second law of motion as well as the first. The stronger the force of gravity is from a planet because of that planet's mass and size, the greater the acceleration the mass of the pendulum is going to experience as it swings. This means it takes less time to swing back and forth when the acceleration of gravity is greater for the planet that you are on. Now, something that is very important to keep in mind is that when we talk about this thing known as the length of the pendulum, it's not necessarily the length that we physically see. It's actually the distance from the swinging point to the center of mass of your pendulum system. Most cases, we deal with a string that has very little or no mass. Often we call it a light string or a light wire. It's a massless string. This means all of the mass is focused at the object at the very bottom. So this is where the center of mass is. So often when we talk about the length of the pendulum, it's what we physically see. But we have things known as physical pendulums. These are pendulums on where the string itself is not massless. It could be a rod, it could be a chain, it could be a very thick or heavy string itself. But when we have to include that mass, the center of mass of the system actually shifts upward, and so the effective length of the pendulum is actually shorter. Rods will swing faster than string pendulums for the very simple reason, since the rods have a mass, their center of mass for the system is closer to the pivot point. So it's not the case that this guy has more mass. It's actually the case that it has a shorter length effectively than this system over here. Now remember, for a rod, the center mass of the rod itself is in its very center. And then we would have to use our center of mass equation, where we have the total mass of the system times the center of mass of the system is equal to the summation of each individual object times its distance from your origin. So we'd actually then have to solve for what this center of mass would be, using this as my origin and using this as half my length for my rod and using the full length for the position of the bob itself. Then I could calculate out what the center of mass length would be to use for the length of the pendulum.